Good evening, everyone. This is Nikita and the co founder of Society for Space Education Research and Development. I welcome you all for the second day of World Space Week program at SSERD. And we have one of the amazing keynote speaker for the day. And let me take the chance to introduce him to all of you. Professor J. Srinivasan is a distinguished scientist at the Vaishya Center for Climate Change, also an honorary professor from the Center for Atmospheric and Oceanic Sciences, that's from Indian Institute of Science. To tell a little more about him, he has done his bachelor's in technology in 1969 from IIT Madras, and then he went on to do his MS in 1971 from State University of New York. Apart from that, he has also done his PhD in 1975 from Stanford University. He has worked in various sectors, but particularly in the field of climate change, and it is one of the important factor in today's world. If you all know the way that the world is changing just because of the environmental changes that we have, and there is a role that satellites or space technology or satellite data playing on these kind of challenges, and at the same time we all know how important it is for us to know what is the weather it is going to be when we step out of the house, or be it before we launch any rocket. So to tell us more about all these topics, I welcome our keynote speaker of the day, Professor J. Srinivasan sir. Can you hear us?
Can you hear me? Can you hear me?
Awesome. Yes, sir. I welcome you to the World Space Week program.
Okay.
Thank you so much for accepting our request and joining us to share all your knowledge, experience, and all your views that you have among all our students. Thank you so much.
Thank you. Can I start the talk?
Yes, sir. You can, and the screen or the platform is yours now.
Yeah, thank you, Nikita. Today I'm going to talk about how you can use satellite data to understand weather and climate. Weather and climate influence our life every day. You want to know what the weather is to decide what you want to wear, or you want to carry an umbrella, and climate for making decisions about what you want to buy for next season. And today there's another concern about climate change. All of us are worried about how climate is changing rapidly and what will happen 10 or 20 years from now. We can understand a lot about weather, climate, and climate change by looking at satellite data. We are lucky that today there are hundreds of satellites going around the Earth, giving us real-time data on various properties of the atmosphere: clouds, rainfall, humidity, temperature, and so on. And an average person can visit many websites and get an insight about what's going on every day. And the best way to learn about weather and climate is by just going to various websites and finding out what is happening. Okay, this is today internet is there, and most of the websites are free. They give you data and images. So let me just give you a guided tour of what all you can do with satellite data. Now we can look at the Earth many ways: through aircraft, through ships, through what they call drop zones, balloons drop downward, or radio sounds which are sent upward, or radar. But the most convenient way to look down on the Earth is from satellite. And today, most of the data we are getting for weather and climate prediction is from satellite. And the first satellite was launched in 1960, 60 years ago. Okay? And they have been helpful to study cyclones, how volcanoes are erupting, episodes of air pollution, spread of forest fires, extreme rainfall and floods, and rapid melting of glaciers. And of course, recently, because of 6 years ago, we know how sea level is rising. So most of this data can be downloaded from satellite images. And this is the best way to learn about weather and climate. Now here is a picture of three cyclones together coming to the coast of Florida in USA about 20 years ago. Before the advent of satellites, these cyclones used to hit the coast without any warning and kill thousands of people. Today, because of the satellite and ability to see cyclones almost continuously, we are able to locate when a cyclone is born and track its movement through the ocean until it hits the coast of any country. So in the last 10 years, we have been able to, in India, track the cyclones very accurately, especially in the state of Orissa, which is subject to many cyclone landfalls, and we have been able to save a lot of lives. So this is one of the great achievements of satellite. Now, climate change is the major issue we face today, but remember, there are other issues also related to climate change. There are environmental changes going on, quality of water, soil degradation, air pollution, ozone hole, and plastic pollution, and so on. Now, all these can be monitored by satellite. So that is the huge advantage. Now, the subject broadly is called Earth System Science. Entire Earth system we study. You can study climate change, you can study carbon cycle, you can study Earth composition, atmosphere composition, water cycle, and weather. Okay, all these are possible through satellite, as shown by this NASA picture. Now, what does satellite measure? Satellite measures radiation, and it measures the radiation coming in from the sun. It measures the radiation reflected by the Earth, and of course, radiation emitted by Earth. All these three are the ones which control the Earth's climate. Okay? So these three quantities are measured, and based on these measurements, we have to infer what's going on inside the atmosphere. So, so just these three values: emitted radiation and reflected radiation at various wavelengths, because every wavelength gives you one piece of information about the Earth's weather and climate. Now, so you have to span the entire electromagnetic spectrum from the ultraviolet below here, right here, all the way to microwave, which is the frequency used by you when talking on mobile phones. So all these wavelengths are useful to us to study what's going on in the atmosphere and the Earth's surface. So each of these wavelengths is utilized by a satellite. Here is a picture of an environmental satellite launched many years ago by the European Space Agency, which has provided a lot of data on air pollution, water vapor, clouds, and so on. And in this picture, you can see the satellite has a very important solar panel which provides power to the satellite, and it has what I call a bus structure on which all the instruments are mounted, and all the instruments have to look downward and see what radiation is coming from the Earth and the atmosphere, and based on that infer what's going on. Okay, so you can see all the parts are marked here: the power source, the sensors and instruments, and of course you have to communicate the information to the ground. You have to transmit the data to the ground, And so the pulse holds all these instruments and the electronics. Now, when the satellite measures radiation, it measures radiation emitted by the atmosphere, radiation emitted downwards and reflected by the Earth's surface, as well as emission by the atmosphere. All the three are coming to satellite, and we need to separate these streams out in order to decide what you want to look at. So suppose you want to look at the Earth's surface temperature, sea surface temperature, then you should be not looking at emission by the atmosphere or the reflection, only the emission from the surface. So you choose the right wavelength, which will give you the data mainly from the ocean surface. Now, one of the most successful satellites was launched by NASA called the Atmospheric Infrared Sounder. Sounder is a name given when a satellite is used to measure the vertical profile of temperature, humidity, and gases. It's a very important quantity for us. And this particular instrument in a mini satellite so far gives you about 3,24,000 soundings per day. That kind of information, and has been going on for 18 years, this instrument. So it has been a very important instrument for us to understand Earth's atmosphere. Now, when you launch an instrument on a satellite, you have two main choices. You can put it in a geostationary orbit, which is about 35,800 kilometers over the Earth's surface, or a polar orbiting satellite, which goes over the poles and comes back. The geostationary satellite is so designed that it has a period of orbit of 24 hours, which means it is same as the Earth's orbit. So it looks stationary when you look from Earth. Because it's moving at the same speed as the Earth, it will be all the time only at one point, so it will see one part of the Earth continuously. So it's very useful to study movement of clouds, movement of cyclones, and many other things. But it cannot cover the whole Earth. It won't cover polar regions, for example. So if you want to cover polar regions, you go to polar orbiting satellite, which has a period of about 90 minutes. That means in 90 minutes it covers the Earth once, but the Earth is rotating. So after one round, it does not come to the same point. It comes to the point a little bit to the east. And so over a period of a day or longer, it covers the whole Earth. So most of the satellites that are launched for environmental application are polar orbiting. But we also use geostationary satellites because we want to continuously monitor cyclones and clouds. And during monsoon, we want a lot of data continuous basis. So we use both. Now, as you can see, because geostationary satellite is very far away, at a height of 35,000 kilometers, the image size is somewhat not as fine resolution as a polar orbiting satellite, which is much closer to Earth. So we have to trade off these two advantages. Here is a picture showing a geostationary orbit and a polar orbit, and we'll look at more about this. Now, in the geostationary orbit, since you're looking at one point of the Earth continuously, you can watch the clouds move. So in the picture on the right, arrow shows the movement of the clouds at various heights. For example, the yellow one is at a height of about 10 kilometers. So we are able to movement of the clouds. And we are able to do that because this satellite is observing a given region continuously. So you take data every, let's say, 5 minutes and see the movement of cloud and track the cloud. It's called cloud motion vector. So this is very important to understand how cyclones or clouds move. Now, the next slide shows the orbits of both geostationary and polar orbiting satellite. Notice that geostationary satellite, depending on where it's located, covers only one small region of the Earth. Okay. Look at over India, we have INSAT. It covers only the Indian region. It doesn't cover many parts of Russia, for example, or America. Americans have their own satellites which cover parts of America. So each country has put up one or two satellites to cover their country. Now, when a polar orbiting satellite goes through one orbit, here it is shown by this picture, it goes like that, goes around, when it comes back, it's slightly shifted to the west, because Earth is rotating in the meanwhile. So it won't cover the same region, it will cover a different region, and there is a slight gap, you can see. That there's a slight gap here, which can be there in some images. Sometimes it is interpolated, you smoothen it out. I'll show those examples. Here's an example of microwave instrument in one of the satellites called AMSU, and you're seeing the radiation emitted in microwave. Land has a higher emission than ocean visibility, so land looks warmer. But notice that these black points are where the satellite did not cover, because after coming one orbit, it went slightly to the west and so missed a small region. This is not very large, so in many applications, they will just interpolate here and give you a nice smooth image. Actually, there's no data there. We need to know that. Now, although most satellites are either polar orbiting or geostationary, some satellites for special applications have a different kind of orbit. The ISRO and the French Space Agency, CNES, launched a satellite called Megatropic 9 years ago, where we wanted much higher observations in the tropics. So that satellite was to study the energy and water cycle in tropical cloud systems by measuring frequently. So for that, we used an orbit, which is shown here. So in 1 week, it covered India 5 times a day. Okay? And it covered all the tropics, not just India. So this is showing coverage over 7 days. It does not cover mid-latitudes or polar regions. It's meant only for tropics. So this special satellite, it's a special kind of orbit. Now, from the satellite, when a sensor is looking, it can look down directly, like one shown here. It measures radiation which is coming up from the Earth and the atmosphere. This is called radiant measurement. This is the most common. But sometimes we want to look at the Earth in terms of slices. So you want to look at the vertical variation. Then your satellite will look sideways here through the atmosphere, and then it will give you the value at a given altitude and will not look down. Okay, so both kinds of techniques are used for different applications. Now, one of the important purposes of satellite is to measure incoming solar radiation. Now, before satellites came, we were not sure whether the sun's output was really constant or was it varying. All of you know that sun has sunspots and what causes variation in the output. So there are a lot of speculation about how much it's varying. But today, because of satellites, we have data over the last 35 years, shows that the sun's output varies between 1365 watts per meter squared to 1366.5, about 1 watt per meter squared variation between the minima and the maxima of the sunspot cycle. This is not much. This is about 1 watt per meter squared variation in 1365 watts. So it's 0.1%. So although this variation is there, it doesn't have a big impact on our climate. There's a small impact, but it's not very large. So fortunately for us, the sun's output is fairly steady. And so if climate is changing a lot, it's not due to sun's output change, but because of some other reason. Now, one of the things which we learned from the satellite measurement was the role sun plays in our monsoon. Now, all of you have read in your school textbook that monsoon is driven by contrast between land and ocean. That's actually a very simple idea. It is not completely true. The monsoon depends upon sun's radiation. So that's why we get monsoon in India during summer and not in winter. Now, how much sun's radiation do we need? Now, that depends upon, you see at the top, the difference between absorbed solar radiation and what is emitted by the Earth's surface. The difference between these two is what is the energy available to drive the monsoon. This must be positive, okay, and fairly large for the monsoon to work efficiently. Now, you can see in this picture in the month of July 1987, satellite measured this net radiation, difference between absorbed solar and emitted, and you see that there's a difference between India and Sahara. Look at Delhi. Delhi is at the same latitude as Sahara. Delhi gets around 60 to 70 watts per meter squared, while Sahara gets only close to 0 watts per meter squared. So Sahara has no monsoon because there's not enough energy there to drive the monsoon. So monsoon in Africa is confined to up to about 15 knots, right here from the arrow. Well, in India, it goes up to the Himalayas. So this particular understanding came only from satellite data, that the net radiation from the sun's radiation, which is absorbed by Earth and after emission, is what drives the monsoon. Okay, so we now monitor this particular quantity very closely to watch how it is changing. Now let's look at the kind of quantities satellite measures. A huge number. I will not cover all these things. I'll just want you to give an idea about how it measures sea surface temperature, vertical profile, soil moisture, aerosol particles, then cloud properties, very important, cloud height, cloud cover, the particle size of the clouds, whether it's ice or water, cloud base, and so on. And it also measures the electrical field in the ionosphere, geomagnetic field. You can measure land surface temperature. You can measure vegetation, total amount of water vapor, ocean color to see whether enough photochromaton is there in the ocean waves, ozone, snow cover, ice, so many things. So satellite are able to measure quantities in the atmosphere, in the ocean, over land, over space, and so on. That's why it's so important to look at satellite data. Now, I've just given you one snapshot of the data from the atmospheric infrared sounder. The kind of product where it can give you a temperature profile, water vapor profile, clouds, ozone, carbon monoxide, sulfur dioxide, methane, carbon dioxide, and dust. Just a sample. Many more things are there. There's a sample. And all of you know that the carbon dioxide is increasing, which is leading to global warming. So we have to monitor this gas very, very closely. And near the end, I'll show you how the satellite can do that. Now, here is the measurement of the carbon dioxide in the atmosphere in July 2008. And you can see that carbon dioxide is not uniform. It is large in some places and small in some places. There are a number of reasons. Carbon dioxide emission, of course, is large where there are industries and urban areas, but then it's also quickly transported to other places. So the carbon dioxide from India, for example, will go over the ocean because winds will carry it. But the idea today is to measure carbon dioxide accurately and then from there try to infer where it came from, who emitted it, which country and which industry. So that is one of the major goals for the next 10 years. Now, the next important property the satellite measures is sea surface temperature. It's very important because that controls Earth's climate. Now, before satellites came, the way sea surface temperature is measured is by buckets. The sailors on the ship would take this bucket, throw it into the water, collect the water, bring it to the deck of the ship, and put a thermometer. Now, this is a very crude method, not very accurate, and you can only measure temperature in a few points in the world, wherever ships are there. Most of the world, there's no ship. So this was a very, unsatisfactory situation. So once satellites came in 1960, techniques were discovered to measure temperature from the satellite, and they are now very accurate. And of course, they are checked against the bucket measurement. Bucket measurements are required for calibration, but the major data today about the ocean temperature come from satellites. Now, if you want to measure ocean temperature, you have to look at that wavelength in the atmosphere which is transparent to radiation. Because if the atmosphere absorbs radiation, then you cannot see the Earth. So there are only a few points. One is visible region, the atmosphere is transparent, but there the ocean doesn't emit radiation, so you cannot use it. You can use some region around 10 micron in the infrared, or you can use a microwave. The micro region is a region where around a millimeter wavelength, where atmosphere is very transparent. That's why your mobile phone uses microwave. And the only problem is microwave radiation is very small. The radiation emitted by the Earth has its highest value at 10 micron. So if you go to 1000 micron, you won't get much signal, but we have to manage with that. We have to somehow use that weak signal to find the Earth temperature. Now here is an example of the sea surface temperature during August, September measured from satellite. Okay. Sorry, this is a measurement of sea surface salinity. They also not only measure temperature, they also measure salinity. Salinity is very important because that determines ocean movement. So here it shows that the salinity is very high in the South Bay Bengal, around 34 grams per kilogram. But you go near the near Calcutta, near the head of the bay, it is very low. Why? Because the river Ganges and Brahmaputra are discharged here, and they make the ocean very dilute. The salinity is reduced. Same thing here from Burma, the river Irrawaddy and other rivers come into the Bay of Bengal. They also. So these two places have low salinity, but rest of the ocean has high salinity. And this measurement was done by a satellite which was able to measure salinity by looking at the sea surface temperature. Now, when you try to measure temperature salinity using infrared radiation, you have a problem that when there are clouds, you won't get any data. So this slide shows the percentage coverage with the infrared sensor over India is only about 50%. Only 50% of the time you can get sea surface temperature because other times clouds are covering it. So that's why you have to use microwave to measure sea surface temperature. Now here is an example of measurement made by satellite showing the Gulf Stream in the Atlantic Ocean, which is warm at a temperature of 25 degrees centigrade and surrounded by cold ocean at about 10 to 15 degrees. This Gulf Stream takes water all the way from Florida to places like England and Europe, and this plays a very important role in controlling the climate of Europe. Okay? So satellites closely watch how the Gulf Stream moves because that tells us how the climate of Europe will change. Now let's look at the sea surface temperature obtained from satellite on one day, that is 21st November. It's a 3-day average. And you can see that the highest sea surface temperature is over the Pacific Ocean near Indonesia, which can go as high as 32, 30 degrees centigrade. Okay? You can also see a region near South America where the temperature is quite low, 19 degrees centigrade. Now, this large difference in temperature between Indonesian Ocean and the Pacific Ocean near the coast of South America has a big impact on our climate. It drives a huge cloud system, and if these ocean temperatures change, it affects Indian monsoon. So this phenomenon is called El Nino because suddenly a warm water appears in the coast of Peru, and when that happens, it has an impact on the Indian monsoon. So we need to study variation temperature both in this region, West Pacific, as well as East Pacific, to understand how the monsoon will behave in India. So it's a very important issue. Now, here's an example that during the year when the east coast of the East Pacific Ocean is very warm, then India in the winter will be warm, and in summer there will be less rainfall. And in the case of Indonesia, it will be both warm and dry, okay, in this region. Now, this slide shows the satellite measured sea surface temperature in the Mediterranean Ocean on the top, and at the bottom it shows the chlorophyll concentration in the ocean, which is very important to understand where the fish will be found. Wherever chlorophyll is high, fish come to go there, and so the fishermen would like to know where the fish is. So it depends on both on temperature and chlorophyll content. So both are measured continuously by satellites. Now, the other important parameter satellite measures is rainfall. Now, on land, you can measure rainfall using the rain gauges. But our ocean, we cannot have many rain gauges. Okay, there are not many human beings there. So you have to measure rainfall ocean using satellites, and this has been done over the last 50 years. And this shows the average rainfall for about a 45-year period. And you can see the highest rainfall is not over India, but over the Pacific Ocean. Okay, about 8 millimeters per day. The average rainfall over India for a whole year is around 3 to 4 millimeters. That's all. And how this pattern changes with season and on different years is very critical for our weather and climate. Now, this picture shows along the equator how rainfall varies from 1988 to year 2000. You can see that there's an annual cycle of rainfall over the Indian region here, around 80 east, and also variation in the West Pacific. And there is a very dry region in the East Pacific, which is very cold. But occasionally you see the rainfall band moves from West Pacific all the way to East Pacific, and this is the El Nino phenomenon. When the El Nino appears in East Pacific, this rainfall system moves from west to east and causes a big impact on monsoon over India and monsoon over Amazon region and over America. So this is what satellite is continuously monitoring to tell people in advance how the weather and climate will change. Now, here's a picture I've taken from a website called Rapid. This is a software developed by ISRO, but it is available in the IMD website. You can see on the top, the IMD website, you can go there. And I've just shown the rainfall as measured by the INSAT satellite on 3rd October 2020, 2 days back. And it shows that the monsoon is almost ending. A little bit of rain is there over East India and Andhra Pradesh. Rest of India rain has almost ended, but there's still rain in Bay of Bengal and in the Equatorial Indian Ocean as well as Indonesia. So all of you can go to the website, and this website gives you a chance to look at rainfall, water vapor, aerosol, and you can look at your wherever your town is and look at how rainfall is varying. It's a very nice software. I want you to go and explore it, and you can look at this website. Just if you don't remember the website address, you just type IMD Rapid on Google, and it'll give you the website, and it is free, and you can use the website to explore how the rainfall is changing on a day-to-day basis, or even hour-to-hour basis. For example, I use this satellite to look at whether it's going to rain in the next 2 hours. Suppose I want to go outside, I will look at the satellite and see where is the cloud band. Is it over Bangalore or is it somewhere else? So it gives you data every few minutes. Okay, very nice website. Now you might wonder how accurate is satellite-derived rainfall. Because satellite derives rainfall indirectly. We're looking at cloud top height and other things. Now here I've compared the rainfall average over 20 years from rain gauges maintained by India Met Department with that measured by satellite, which I will mention later, called the Global Precipitation Mission, GPM. And you can see that we are quite good. It looks similar, except on the west coast of India, the rainfall measured by rain gauge is higher than that measured by satellite, because this rainfall is not a normal one. This rainfall occurs due to Western Ghats. This rainfall has a different structure, and the satellites have some difficulty in capturing that. Otherwise, satellites are able to give a very nice spatial pattern rainfall, and you can get this in near real time. So you look at this website, which I'll show you later, you can look at rainfall in the last 3 hours, for example. It will give you animation, give you actual value. It's great fun to look at this website. Here it is. So you can look at this website. It is gsfc.nasa.gov, and it was given you on 4th October yesterday at 7:30 a.m. Eastern Daylight Time in East Coast of America, and it shows these rainfall systems in various parts of the world. Okay? In India, you can see the same system I showed earlier, the East Coast of India and Bay of Bengal, and the Equatorial Indian Ocean, Indonesia, but it shows the global picture. You can see the ice over Greenland, ice over Siberia, ice over Antarctica. It's very nice, and it has animation. So that animation shows you how these systems are moving. Now, this mission, GPM, uses about 10 satellites, not one. Okay? One of them is Megatropics, Indian satellite. It has a core observatory which has a radar, which is an active sensor which sends beam radiation to the surface and looks at the reflected radiation, and lots of other passive sensors, those which contain instruments to measure radiation passively, not actively. And it combines all the passive and active sensors to give an accurate data of rainfall every half an hour. Okay? So this is a very amazing mission which involves cooperation between all nations of the world. And so this is the way now satellite technology is going. Every nation puts out one satellite and they share data, and all the shared data is gathered and combined to give you a new product. This is a photograph, artist photograph of the global President mission, and you can see this is the core observatory containing a radar and the solar modules, and the details are given here about the radar they use, and also passive microwave images. Both these are combined to give you rainfall. Here is an animation of the rainfall obtained from the satellite. This is for the month of June, daily rainfall. You can see how the rainfall systems are moving from Bay of Bengal into India. Okay? And you can watch it slowly and understand how cloud systems move, how India gets rainfall from either Arabian Sea or Bay of Bengal. Okay? This is a wonderful thing. Either you can look at their graphics or you can download the data and do your own animation. Now, the next important data, which is what we're looking at, is water vapor, and it's measured in various ways. You can measure water vapor passively using microwave or infrared or visible, or you can use active sensors, send your own beam of radiation and like LiDAR and look at water vapor absorption. Okay? Now, next slide shows the animation as provided by the University of Wisconsin website, which you can look at the top. This shows how water vapor in the whole column of the atmosphere varies in time. This is 1 day's data in the month of October, 3rd October. You can see how the water vapor is moving and how water vapor is brought from southern hemisphere into northern hemisphere by the winds. Okay, so this is worth watching over a period of time to know whether rainfall will come to your region, because first water vapor has to come to your area before it can rain. So water vapor is a precursor to tell you when it will rain. Okay. The next picture shows a bigger picture, a snapshot on 2nd October, showing how water vapor moves from the tropics all the way to 60 degrees north, like a nice little arc. It curves around because of Earth's rotation, and this curvature is very nice. And you can see how water vapor is transported from the tropics all the way to mid-latitudes in thin filaments. Okay, it's very nice to watch. It's a beautiful animation you can see. Now, the next picture I've shown you from a website called Windy. It's a very nice website. it's meant for weather forecasting purposes, but also gives you satellite data. So on 22nd July this year, it showed a very nice east-west oriented cloud. This is the cloud top temperature around 200 degrees Kelvin, and you can see it's east-west orientation from Bhubaneswar to Mumbai, and this is called intertropical convergence zone. This is the east-west oriented cloud band formed every year, and this cloud band brings the rain to India. And so this system, it moves all the way from equator to this region during summer, and we watch how it moves to understand how monsoon rain evolved during the summer. Okay, so this is a wonderful website. There's nice animation, and you can look at what happened to the cloud in the last 10 minutes or last 2 hours. Okay. Now, as I told you, cloud can also be used to measure motion in the atmosphere, and this shows from the GO satellite launched by the Americans, geosynchronous satellite. It shows the cloud at a height of around 15 kilometers, the red arrows there, and the yellow arrow shows cloud at about 3 kilometers, and green shows at a height of around 6 kilometers. All these are telling you that clouds at different heights are moving in different directions. Okay, and the website here is a COMET website, which is part of the WMO, World Meteorological Organization. Look at this. It has lots of nice both images and information called SatMet, Satellite Meteorology. So any of you interested in this topic can go to COMET website and get lots of information. Here is a close-up of the winds as obtained satellites by different satellites, Meteosat of the Americans, GMS of the Europeans, goes against American and so on. And all the satellites giving you winds all over the world except the polar region. Okay? So this satellite, which is geostationary, cannot see the polar region. And satellite also gives you fires. Tells you, in the last couple of years, lots of forest fires have occurred in California, all of you know that. And it can measure both fog and smoke. Fog is brighter, smoke is dull. You can differentiate between fog and smoke. And so this is used to monitor how fires spread in different parts of the world. And this is from the Worldview Earth Data, the wonderful website of NASA. So go look at it and watch the fires as they evolve. Another picture of the winds, which are shown already. This is another close-up in the Pacific Ocean. This is over, yeah, you cannot see it, yeah, this is over the Pacific Ocean. Now, you can measure winds from satellite using clouds, but what do you do when there's no cloud? It's very clear. For that purpose, recent European mission, European Space Agency, launched a very ambitious satellite called Aeolus, which is a name for the ruler of the winds in the Greek mythology. Like we have Pavan in India, there is in Greek mythology a god for the winds. And this is a satellite very, very sophisticated, very expensive. It uses a laser. A laser beam is sent down, and the scattering of the radiation from the laser beam is used to measure the wind direction and magnitude using a concept called Doppler shift. Some of you may have heard of Doppler shift. You do a Google search, you'll find out that if a particular air mass is going away from the laser beam, then the frequency will change. And that is measured by satellite. So this is the artist image, how the satellite beam is coming down and how it measures the scattered radiation. And so this has been very useful to measure wind over clear regions where clouds are not there. Now today, one satellite is not enough. One satellite cannot carry all the sensors because there's not enough space on satellite. So you use a constellation of satellites, not one satellite, 6 or 7 satellites on the same orbital plane at different times. Here is an example of the American Aqua train, which has 1, 2, 3, 4, 5, 6 satellites, one behind the other, about 1 minute behind each other, okay, on the same plane. So the same region is observed with different sensors by a constellation of satellites, a very remarkably complicated operation. So this is going to happen more and more. One satellite measures gases, the other one measures aerosols, the other measures clouds, and so you combine all of them. Okay? One measures carbon dioxide, you measure all these quantities and integrate them. Now, all of you know that carbon dioxide is increasing and it is reaching harmful levels, so we have to monitor it very closely. So recently, the American launched a device called the Orbital Carbon Observatory. The first one was launched more than 10 years ago, but it failed. The second one, OCO2, was launched recently, and it is able to measure the difference in carbon dioxide concentration over urban region near Los Angeles and a rural area. Urban areas has about 400 parts per million. The rural areas has around only 390 parts. So this difference shows you where the carbon dioxide is released in the atmosphere. So we know that Los Angeles is the source. So this is going to be used to monitor CO2 emission. And so this is going to be launched, many more will be launched, and every nation will be monitored for their CO2 emission. And here is a picture of the CO2 in various parts of the world. You can see there is more CO2 where there are people and where there are industries. And over ocean there's less, sorry, this is methane, not CO2. Methane is there more over India and Africa and America. Over ocean there's no methane, because main methane emission comes from rice and cows and human activity. And so this is used to monitor methane. And the other important thing is lightning. Lightning is kills many people who work outdoors, like farmers and others. So today, satellites carry a lightning sensor. You can see that the number of lightning flashes per kilometer square is the largest over Africa. It's also large over India and America and South America. So these are now monitored very closely. And here is a close-up of lightning for a 3-hour period over Australia. And so this is a very important instrument for monitoring lightning. Now, the other important thing is ozone hole. All of you know that ozone layer in the stratosphere protects us from harmful ultraviolet radiation. And this was measured by satellite. Without satellite, we would not know about the ozone hole. And ozone has two portions: a good ozone, which is there in the stratosphere, and a bad ozone, which is near the ground, which is bad when you breathe it. But I'm talking about the good ozone in the stratosphere. And satellites show that over Antarctica, where not many human beings are there was a huge hole due to human release of chlorofluorocarbons. So they were able to show that, and after that, a protocol was signed by all nations to control the release of this awful chemical. Okay, and satellites are also used to measure floods. So about 10 years ago, there was a major flood in Pakistan. In the Indus River flooded, and this flood is seen by a microwave sensor in the region. Here you can see that the normal Indus River is shown in a thin blue line, and when it flooded, it broadened out and caused a lot of problems over various parts of Pakistan. Okay? And where it discharged, also you can see a change in emissivity of the microwave. Now, the other thing satellites have measured is the melting of the Arctic sea ice. Arctic sea ice is a very large area, and that has been continuously falling. Okay. Hello. Yeah, the last part I want to talk about is occultation, which measures the concentration of a minor gas by sliding the atmosphere. Okay. It's called Limsonian occultation. And this, of course, I've shown the further satellites. And of course, satellites also measure aerosols. Here is a picture of aerosol measured by one satellite over North India in winter. You can see a large amount of aerosol coming from the Indo-Gangetic Plain into the Indian Ocean, into the Bay of Bengal. And also the large carbon monoxide pollution over India and China in winter. Okay, and here is a close-up of the sulfur dioxide emission over the power plants in Chhattisgarh and Jharkhand. And so these are the ones which are the emission from all these industries. Satellite can also measure wind because wind struck with the ocean causes foam, and this foam can be measured from satellite. And so these are used to measure surface winds over ocean. Now, since I come to the end of my talk, let me conclude by saying that you can learn a lot about weather and climate variability and climate change by looking at various websites maintained by weather and space agencies of different countries. You can download data free from many websites, make your own graphics, and it's a very interesting way to understand weather and climate. I hope I gave you a glimpse of what you can do, but you need to go and make your own attempt to understand this. And if any of you have any doubts, you can send me an email, and I will be happy to explain the various ways to understand weather and climate. Thank you.
Thank you. Thank you very much, sir, for that such a detailed explanation on the topic that you had chosen to give, and which is the important thing I also feel. And we have few questions. We'll just take like 2-3 so that the audience don't feel bad. And here you go. So the first question is, what is the blind spot of a satellite, or does that affect knowing the weather in any ways, is the question.
Yeah, the word blind spot, it occurs in many ways. Sometimes when the sun's radiation reflects off the ocean, there's something called glint, G-L-I-N-T, glint, and that causes error in measurement. That's one thing. The second thing is, all of you must have seen when you're watching cable television, when the sun's radiation is aligned to the antenna of the satellite, you lose signal. So that's another blind spot. And the third one is what I showed you. Between two parts of a satellite, there is a region where we get no data. So there are three different ways in which you miss the signal, so that's a blind spot.
Great. Thank you very much, sir. And there's one more, I think, very important question for all of our students to know. How accurate are these weather predictions made by satellites? Like, out of your experience?
I can tell you, it has improved dramatically in the last 20 years. The best way I can tell you is, don't believe me, go look up those websites today or tomorrow and compare your judgment. Look at the rainfall, let's say tomorrow in Bangalore, and compare with what it's saying today. So 1 to 2 days forecast is very good, but of course we can't forecast 10 days in advance. That is tough. But forecast of tomorrow and day after is very accurate. For example, satellites are saying there will be no rain tomorrow in Bangalore. I can guarantee there will be no rain. Okay? And as a matter of fact, today satellite is used to measure how much yield will come from a solar power plant, because you can measure radiation coming on the ground and forecast it accurately. So I can use satellite to tell how much solar power plant will generate tomorrow. Okay? Yeah, so 1 to 2 days in advance, very good. But if you want to know what will happen in the month of November, that's not easy. That's tough. We are still working on it, but it's not easy. But 1 day, 2 day, 3 day forecasts are excellent. But I want you not to believe me. Please go look at the website and have fun watching the forecast with your own actual observation outside your home or office. Okay? It's a great, what you call, today, many of us are trapped in a house due to COVID. It's a great pastime. You just look at various satellite predictions and go out and see what's happening. Okay?
True. I totally agree to you, sir, because we actually get the notification telling, okay, 5:02, you can expect a rain, and you go out and you see that it would have started raining. For sure, sometimes it might not be in the exact place where we are, but somewhere around it would have started raining. And I see that it's almost almost right, and I think a little bit is always there, but yes, it's good to know that they're all like very good in prediction. This is
Yeah, you're
again out
right.
of my
Yeah,
curiosity. uh, the weather that like the weather updates, like for example, if we have to know how is it going to be, um, like roughly we get to know exactly. Okay, let me tell it in this way. So if I have to go check out the weather, it actually shows me accurate weather for next 2 weeks or something, right?
yeah,
And
but
then
the accuracy goes down. See, you're right. Every weather agency predicts 2 weeks of weather, but the accuracy goes down as you go further. So, for example, if the prediction is that next Monday it will rain in Bangalore, it's not that accurate. Okay. So as you go far in time, the atmosphere is chaotic in its behavior. So, but tomorrow's forecast is very good. Day after is very good. Third day is good. Slowly it decays. Okay. And and there are websites which will give you what they call verification. They put out how good they are. So you can look at it. And
true.
all of you will learn a lot by, it's the best way to get educated about satellites, about weather, about climate, by watching the forecast of different agencies, okay? And the best one is when there's a cyclone. Cyclone track prediction is very accurate. That's why we are able to save lives in Orissa and West Bengal this year. So watch it, it's great fun, and it's a great way to learn a subject, okay?
True, true, true. So there's one last question which we will take and then we can end. What is the approximate size of data given by these satellites per day, like particularly weather
Oh,
satellites, weather
I
forecasting
mean,
satellites?
it is in terabytes. I have a slide which then I didn't show. It's huge. I mean, you won't believe, that all the weather forecasting agencies download this data in real time and assimilate it. That is, put it into the model. So our models are not accurate. So you tell the model where is the cloud, where it's raining now, and that is helpful for the model to correct itself. So they, I think, download hundreds of terabytes of data in a matter of few hours, and the model is able to use that to correct itself. Okay? And and if you want actual data, I have a slide, I can send it. It's a huge amount, and it has increased in the last 10 years. Because all weather agencies have their own satellites, and all the data is shared. That's one thing good about uh, world space and weather agencies. They, although we fight with each other over minor issues, but on this issue, there is cooperation. Weather data is shared, satellite data is shared, so we get data from Africa, China, America, and Europe in our weather agency. So because of that, all of us benefit. So this is one good example of why we should cooperate. If we cooperate, we'll get more. And sharing data freely is the greatest achievement of this present era. Okay, it was not there when I started work 30 years ago. Data was not available easily. Today it's available free, and you should use it fully. If you know software, you have curiosity, there is infinite amount of data available. Okay?
True, true, true. I totally agree to everything you said, sir. And I want to highlight that the fact that you said it's available for everyone, and it's not just limited for those who are working in this field. It's available for all of us. We could anytime go check out, and in fact, you yourself can start predicting. That is something
Yes.
that I learned out of this session.
Yeah.
So thank you very much, sir.
Yeah. As a
And
matter of fact, there are many blogs. All of you, there are many blogs predicting Chennai weather, other weather. You can also start a blog giving your experience about how the weather is predicted. Okay, great fun to communicate with people all over the world about weather in different parts of the world. And yes, it's a wonderful way to learn.
thank you very much, sir. And it's a very huge thanks from the whole audience and SSERD team for you to come over and spend a lot of time with us by sharing your experience in this domain. And this is really going to help all our audience. So, audience,
Let
you
me, yeah,
understood how.
let me just tell you that this 1 hour is not enough. I teach a 14 lecture course on satellite meteorology. 1 hour for me is too short. So if your audience wants similar lectures on a specific topic, I'll be happy to give. Okay.
Awesome, sir. Thank you.
Okay.
Thank you very much for extending that warm welcome to everyone to learn more and more and explore. So, thank you very much. And I was telling all our audience that this is one of the important thing. I think I'm telling them from the beginning because it is important. So, go explore. And this was today's keynote by Professor J. Srinivasan on the weather and climate with the help of the satellite data. So thank you so much, and stay tuned for another keynote tomorrow. Bye bye.
Okay. Thank you.